So let us continue our topic, and let's go to the integrals of the type 3. And it will be just simply, we assume that we have here a given function, so that means compute the following improper integral. And here the integral looks like this. This is from minus infinity to plus infinity. And we write it down. This will be e(i)ax. And here we put here f of x dx. We will assume that a is a positive constant. And we have the following assumptions. The function f of x, which I'll write simply as a p of x divided by q of x, is a rational function and here, of course, we have p of x and q of x are polynomials, so we will assume that q of x is different than 0 when x is real, so that means there are no singularities on the real line. And the third condition C, is that the degree as a polynomial of q is larger than the degree of p. And then you should easily notice that the condition C implies that limit, and put here maybe star for that one, as z in modulus goes to infinity of f of z is equal to 0. This would imply it. So let's present the method. So let's write it down. Solution using this method. Solution. And we will be doing in a very similar way as it was done in the case of the integral of the type 2. Namely, we consider maybe, first of all, consider the equation, and that means we are looking for the singular points, and I put here z is equal to 0, so that means we are looking for the singular points. Okay, let me put it like this. We are looking for the singular points. All of them will be poles because q is analytic, and that means that the zeros of analytic functions are poles. We are looking for the singular points of f of z. And then, of course, let's make a picture. Our situation is very analogous to the previous one. So here we have the real line. Here we have the imaginary line. And then there are no singularities, so let's write it down. Q of z is equal to 0. It gives you possibly several, let's say, solutions. So what do I have here? suppose I have here one solution here, because q is here, it's a real, let's say, this is a real polynomial. It's a real, maybe I mentioned clearly, a real rational function. That means in such a case, those are the real polynomials. So if you have here a non-real, you see q has no zero solution. So that means every root of q appears in the version like you have here one root here, another one is conjugate. So another one, suppose is here, and suppose the other one is here. So we can have many roots and of this equation, and that means those are the singular points. And now, similarly as it was done in the case of the integral of type 2, so we will ignore this portion. We only look at the roots which are in the upper plane. So since these roots are located in the, let's say there are finitely many, so we can choose a number r large enough. So here is the r, and we can take the semicircle going around those roots, and then we close it, and this one is the segment here called the segment minus RR, and this one is the semicircle KR, and we are considering exactly in the same way as we did before the contour. We put it like this, the contour C, and put here R will be like a semicircle R, and union, so we usually put here plus, so this will be like a minus R and R, which is just a linear segment on the real axis. So now we can simply write the formula. So let's write the formula for the integral. So we are interested in this integral. So let me write it down. We are writing down, this is integral CR, and I take the function which will be EIAZ. This is our function that we have here, and this is f of z dz. So since, as you can see here, all the roots in the upper plane of this, let's say, all singular points are sitting inside that one. So if I take another number, for example, take capital R, and I go here, and this is my capital R, and if I change that one, okay, to the bigger circle, you see the value of integral will not change. It is by the Gauss theorem. This will be still the same. So that means this value of this integral doesn't depend on the choice of this number R, as long as it is sufficiently large. So I can say now that here we can write it down that this will be independent of this R, and I can write it down by the residue theorem. This will be equal to pi I, and then you have here sum, and this is imaginary part of zk is positive, and this will be residue of EIAZ f of z at zk. So this will be the residues. So that's integral. That's by term. It can be computed from the residue. So what happens on the right-hand side of this? What happens on the right-hand side of this equation? I can use the formula. That means the formula that tells me that if you have contour, you can split this integral into two integrals. So you are getting first integral will be kr, and then and then you have here E, I, A, Z, F of Z, D, Z, and then go to the next line, and then you have here plus, and this will be, interestingly, because the function f is real, so that means this will be exactly the integral from the minus r to r, and that one will be E, I, A, X, F of X, dx. So that one is this integral. And now I'm interested to find out what happens if I take the limit as r goes to infinity. So let's see. So I claim, okay, it's clear that the second integral, this one is, let's call it my first integral, this is my second integral, so the second integral, just by the definition, it will go to the minus infinity, infinity. This will be E, I, A, X, F of X, dx. So let's find out what is happening to the first integral. So the first integral, so put it like this, notice. Notice, and this is my first integral, that this first integral, I can actually estimate like as follows. I take this integral, this will be kr, E, I, A, Z, F of Z, dz. So we have here parameterization. Remember that z here is equal r, E, I, t, where t belongs to 0, pi. Okay, so let's plug it in. Plug it in. So what do I get here? I'm getting here, this will be integral, and that one will be 0, pi. Then you have here E, I, A, and I can put here e to the power I, t, and that's this part here, and this is f of e, sorry, I forgot something. R. So what is z? It's, maybe I change the color to make sure that it's everything. So this is my z. So I replace it with R, E, I, T, and then you can have it here, F, and it's also, I just put here R, E, I, T, and then we have here derivative of Z, so this will be I, and this will be R, E, I, T. And dt, maybe I should squeeze a little bit better. I, E, I, A, R, one moment. I, R, E, I, T, D, T, close it. Very good. So that was. Now we can use the next one. We can use the inequality, and let me say it like this: smaller equal. Enter with the absolute value inside. So of course I'm getting here. This is f of R, E, I, T. Very good. Then that one just becomes R. So I put here R. And here, in the case that one, I put absolute value. This will be E, I, A, R. And this will be cosine T plus I sine of T. And then you have here, this will be dt. And now I can pull it out, and I say, oh, this is basically from the circle, you know, this is your z, and that one is your modulus z. So we have here that this z is from exactly this circle. So this is your z sitting here. So in such a case, I can just simply estimate like maximal value for z is equal to r. So maybe put it nicely, r. And now what do I take? I take this one, I take that one, this two, no, just this one. So this will be nothing else, and this will be f of z. So see, that was f of z absolute value. So put it here, maybe. So that one. And then times, and here we have integral 0 pi, r is still here. And notice that only this is modulus. So that's a modulus. So here only the real part plays a role. The imaginary part gives you of that number here. This will be your imaginary part. This will give you 1. So I'm getting here minus. This is minus, so put it here. I'm getting here e to the minus a r, and this will be sine of t. A r sine of t minus, and then I put here dt. Very nice. So I'm still estimating. So it is a little complicated, you see, but it's not so bad. You actually, what we can do now, we can just simply change the variable in this integral. I just put here s is equal t minus pi over 2. So let's do it. Let's do it. So this integral becomes now, is just again, this is again equality. Z is equal to r. This is f of z. And then this integral becomes minus pi over 2. This one is pi. That one is equal to r. And that one is equal to, this one is equal to e minus a r. And sine, of course, becomes cosine of t. And we are getting here, of course, this is pi over 2. And we are getting dt. And now I see, this is an even function, This is even function. So if this is even function, then I can just simply write it down, this integral, as a maximum. Again, the z is equal to r, f of z. And then this will be 2 times from 0 to pi over 2. And that one will be r, and that one is equal to, e minus a r, sorry, cosine of t dt. So let's do another change of variable. This time I put it like this. Maybe I should be more careful. This will be t becomes s, and this will be ts. And now change another change of variable. This time I substitute that s is that t is equal s plus one second. Okay, minus pi, and what do I get here? This becomes cosine, so this is plus pi, so this will become sine, and so cosine minus sine, and cosine plus, so this will be becoming, yeah, actually, I think it is this one. Yes, I think we have to do that one. So that this is 0. So okay, check out. what is happening? So if you take, so that means S is equal pi over 2 plus t. So what do I get? The cosine. So cosine, this is 0, and then you have your plus, and this is sine is 1, and this will be sine. And then I'm getting here that 0. Did I do it? Okay, this should be done very carefully. So let's make sure there are no mistakes here. So I go here, and let's see, what do I get here? So clearly, if t is pi, so then this becomes pi over 2. If this is 0 pi, that's okay. And then you have here, let's say, sine of s. Sorry, sine of t becomes sine of. So this is sine of s times cosine of pi over 2, and this is plus cosine of s times sine of pi over 2, so it's 1. Very good, so this one is correct. It changes to s. S, of course. S, and this one is s. Very good. So this is s. Okay, so now I want to go back to sine. So I take that value. So t is replaced. So let's see what I'm having here. I'm having here that cosine of s is equal cosine, and this will be sine. So this will be minus, and this will be sine of t, and this will be called sine of pi. So this will be t minus, definitely minus. 1 second, is t is equal? Yes, very good. That's this one. So I'm getting here, this is minus sine of t, minus sine of t. Okay, so let me write it down. So we are getting here, after this substitution, that means that cosine of s is minus sine of t. And now we come back to this integral, and we can continue. This one is equal, and we have here maximum z is equal to r f of z times 2, and this one becoming, okay, take 0, you're getting pi, so this becomes pi over 2, this one is 0, this one is r, and that one is equal to, and that one is equal, put here like this, minus coming from this one, so this one will be equal to e minus a r sine of t dt. And now change the order of the, let's say, switch the limits of the integral, and you are getting here that max z is equal to r f of z times 2 times 0 times pi over 2 r e minus a r sine of t dt. And the next step, I go here on the margin and I take the function sine. So my function sine is looking like that. So this is pi over 2. So that's my function sine. So I can take this line joining to these points. So the first one is sine, and that one is just simply 2 over pi, 2 over pi t, and you can see clearly that on this interval you have here that 2 over pi t is smaller equal than sine of t, and that implies that you can write this inequality continue. This will be maximum z is equal to r f of z times 2, and here I have here 0 to the pi over 2. This one is r, and this one is e minus a r. And now I put here 2 divided by pi t dt. And now this integral is computable. So that means you can actually evaluate it. So this is z is equal to r f of z, and put here this 2 in the front so it doesn't bother us too much. And then this integral has antiderivative. I can add here, this will be r, and then I have here integral, and put here like this, this will be minus a r 2 pi, and then this one is minus e a r 2 pi t, and taken from 0 to pi over 2. Okay, let's compute it. So this will be again 2, and this is maximum. Z is equal to r f of z times, and now we have some simplifications. So namely this guy cancel that guy, and then the reversion of the orders gives me that one, so I can write it down. That one can be produced like a pi, so this will give me pi over 2a, so this is pi over 2a, and the other one here, that one gives me 1 minus e to the minus ar, and since a is positive, this value is always smaller than 0 here, so that means I'm getting here, maybe after some additional simplifications, this and this, I'm getting here that that one can be written. It's actually smaller, equal than this value, so put it here. So this is pi over a, because that one is smaller than 1, times maximum z equals to r f of z. And now let's go to the condition star. Oh, that was the loss of word star, which is this one, and you see this condition tells you that the limit is 0, so we are getting here that that value is going to 0, so you can immediately notice that here that will be actually coming from the 0 from this first integral. So that's exactly the integral we are trying to compute, and we have now the theorem. Put here like this theorem. And just write the formula, this integral minus infinity, infinity. And then this is e, I, a, x times f of x is equal to pi I, and then you take the sum of the residues for imaginary of zk is larger than 0, and this will be residue, and this is e I a z. That's kind of important. Remember, don't forget this term here, and then you have here f of z zk, and that's the formula we derived. This is the formula. So now let me continue with the examples, and the example is number 5. So let a be larger than 0, compute the integral, and our integral is just simply integral, which is equal minus infinity, infinity, and I put here e I a x t, maybe put it like this, or x, put it like x divided by 1 plus x squared dx. So one can easily notice that the conditions that we require A, B, C are satisfied, and here we can write the answer. So answer, and we can write it down that this integral is equal to EIAX 1 plus x squared dx is equal to pi I, and this is the residue of the function EIA z divided by 1 plus z square at the point I, as this is the 1 plus z square is equal to 1 plus z plus I, z minus I, and that's almost the answer. Now just you need to evaluate it properly. So the residue is equal, this is E, I, A, and you put here I divided by 2I by the obvious formulas that we were practicing before we started this lecture. That means we know how to compute this residues. Cancel. And the answer is, this is equal pi divided by EA, and that's the value. And now maybe notice that we actually have something more interesting, namely that if I write it down that this is the answer, P e to A, and I write this integral, but now I write the values, that one, this will be cosine AX. That's exactly the value here that I'm writing, and this will be plus I sine AX, and this is x squared plus 1 dx. Then you can split into the two integrals, and you are getting here the first integral cosine AX, and that one is equal x squared plus 1 dx, plus an imaginary part is I, and here we are getting here minus infinity, and this will be sine AX, x squared plus 1 dx. So actually this value is equal to this real integral, and that integral of course is 0, and that one is equal pi over e to the a. And maybe it's a good idea to reformulate it as a new theorem, and this will be theorem, because actually this is a general observation, and we can say like this. In this case you can write it down minus infinity under the same assumption, under the assumptions, under the assumptions A, B, and C, the cosine of AX divided by, this is cosine AX times f of x dx will be equal to the real part, and this will be 2 pi I, and that one will be imaginary of zk larger than 0. This will be the residue E I, maybe emphasize it also z f of z zk. So please remember, this is that value, it's not cosine, it is AIZ, and similarly we are getting here that minus infinity of sine AX f of x dx will be equal to the imaginary part, and this will be 2 pi I, and here we have imaginary of zk larger than 0, residue, so this is residue e I a z f of z, and that one will be zk, and that maybe is a good moment to stop. I'll try to add one or two examples to this material, and we'll discuss additional possibilities for these types of the integrals. And thank you for the moment. We will continue with the lecture 10. Thank you. That's the end of the lecture 9.